I'm Brian Hughes.
And I'm Antoine Savine from Superfly Analytics at Danske Bank.
In this presentation, Brian and I expand the differential machine learning ecosystem introduced last year and discuss a couple of very simple and useful algorithms based on differentials computed with AAD. Agent differentiation, or AAD, is one of the most disruptive technologies of the past 10-15 years in the financial industry. AAD gave us automated, analytic, and computationally efficient risk sensitivities and enabled new research that was unthinkable before. In Danske Bank, where AAD is implemented in production since 2015, millions of AAD sensitivities are computed every day, and this massive amount of differential data can be leveraged in a powerful manner with adequate algorithms. In particular, we are going to leverage differentials to correctly reduce the dimensionality of financial models. After briefly reintroducing differential machine learning and discussing dimension reduction in the context of financial models, we will try to convince you that classic principal component analysis is not a safe or effective solution for derivatives risk management, introduce differential PCA, in our opinion, dimension reduction done right, and conclude with important applications. Brian Hughes and I introduced differential machine learning last year in Risk. Differential ML is a collection of new algorithms based on derivative sensitivities in the context of pricing and risk. Let me introduce the main notions in the simple context of a linear regression. This is certainly not the most powerful application or the most novel one, but there I can introduce differential ML in its most simple form. Recall that linear regression considers n input variables xj collected in a vector x along with a target variable y and approximates y by a linear combination of basis functions phi of x with fixed weights beta. Linear regression works with a fixed collection of k basis functions, for example polynomial or spline basis functions. The weights beta are estimated on a dataset of m independent realizations xi of x and yi of y. Regression minimizes the mean-squared prediction error on the dataset, and the solution is given by the celebrated normal equation. Beta is the inverse of c phi phi times c phi y, where the two covariance matrices are estimated on the dataset, and the inversion is best performed with SVD to stabilize near collinearity. Linear regression is prone to overfitting. Overfitting is generally mitigated by so-called regularization techniques, the most common one being Tikhonov regularization, also called ridge regression, which penalizes large weights in the optimization objective with some strength lambda. When lambda is small, ridge regression reverts to classic regression, and so it is prone to overfitting. When lambda is large, the penalty overtakes the MSE, so optimal weights converge to zero, and predictions eventually lie on a horizontal line, a phenomenon known as underfitting. This is an example of a well-known bias-variance trade-off. In practice, a sweet spot must be found, generally by cross-validation. Like classic regression, the solution of a ridge regression is analytic and given by an adjustment of lambda times identity in the normal equation. Differential regression is based on differential labels z equal dy dx, the gradients of labels y with respect to inputs x. Assume for now that those differentials zi are part of a dataset. We will see shortly how we can compute them. We also define phi j, the vector of the partial derivatives of the basis functions phi with respect to the jth input xj. Let me clarify with an example, a cubic regression in dimension 2. The vector phi of basis functions is of dimension 8, where we have 1, x1, x2, x1, x2, x1 square, x2, and so on. Phi 1 is the vector of partial derivatives of phi with respect to x1. The derivative of 1 is 0, the derivative of x1 is 1, the derivative of x2 is 0, the derivative of x1, x2 is x2, and so forth. Similarly, phi 2 collects the partial derivatives of phi with respect to x2. The minimization objective now combines classic value errors with derivatives errors. Like regression, we have hyperparameters lambda that control the relative importance of differentials. In other terms, the strength of a differential regularization. Unlike Tikhonov, however, differential regression does not introduce bias or the risk of underfitting, so dependence on lambda is generally very limited. A reasonable default is given by the ratio of variances of y to zj, and we never had to modify it. Like classic and rich regression, differential regression has an analytic solution, whereby the normal equation is adjusted with the covariance matrices C phi jj and C phi zj, also estimated on the differential dataset. Like classic or rich regression, differential regression is intractable in high dimension. In low dimension, however, it learns pricing and risk functions efficiently with a modified normal equation. The implementation is remarkably lightweight, no training on GPU, cross-validation, or iterative optimization of any kind, just a drop-in replacement for linear regression. It is also very effective, at least in low dimension, as we are going to see, and this is because it reduces variance without a bias. Let me show you a basic example where we learn the Black Scholes pricing function from a simulated dataset. The initial state x is the initial spot, evenly sampled over some interval. The labels are payoffs independently sampled in the model with initial condition x. Note that we don't learn from prices, we learn from payoffs simulated on only one Monte-Carlo path. The reason is that prices are generally not analytic, unlike in Black Scholes, and expensive to compute, for example with nested simulations. By contrast, to simulate one Monte-Carlo path is inexpensive, even with complex schedules of cash flows in sophisticated models. The entire training set is simulated for a computation cost similar to one pricing by Monte-Carlo. Differential labels dy dx are partial derivatives of the simulated final payoffs with respect to the sampled initial states, and they are easily computed analytically in Black Scholes. In the general case, they are efficiently and automatically computed by algorithmic adjoint differentiation or AAD. So, in the general context of an arbitrary schedule of cash flows, like an exotic derivative or a trading book, and an arbitrary simulation model, we independently simulate training examples by first sampling the initial state xi, then sample one Monte-Carlo path in the pricing model with initial condition xi, read the payoff along this path and call it yi, and compute the gradient zi of yi with respect to xi with AAD. If you already have a generic Monte-Carlo engine with AAD, you can just reuse it for the simulation of its datasets, and you get guaranteed consistency with front office pricing, which is an important consideration in the context of regulations like XVA or CCR. We have demonstrated that ML models trained on these tractable but noisy datasets converge towards the correct pricing function all the same. So we proceed with polynomial regression of degree 5 with a purposely small dataset of only 200 simulated examples, so we can easily visualize bias and variance when we compare classic, rich, and differential regressions. Note that rich regression is optimized by cross-validation. As expected, the predictions of linear regression have this wiggly shape, characteristic of overfitting, and significantly change in response to the noise in the dataset, highlighting a high variance. Tikhonov regularization reduces variance, but at the cost of larger errors, highlighting bias. Differential regression, by contrast, has low variance without bias at all, and without cross-validation. Black Scholes is a very basic example in dimension 1. As an equally simple example in higher dimension, consider a basket option in the correlated Gaussian Bachelier model. The dimension n is the number of stocks in the basket. And we know that under the Gaussian assumption, the option really only depends on the initial basket, irrespective of single stock prices. So this is really a problem in dimension 1. But here we purposely perform regression on the multidimensional state to see how regression scales in higher dimension. We use 1,000 randomly sampled examples. In dimension 3, linear regression struggles. Tikhonov regularization helps a bit, but the performance of differential regression stands out. Differential regression really shines precisely in situations like this. Performance starts deteriorating in dimension 5. This is also where neural networks start outperforming linear regression. In dimension 7, performance further deteriorates in addition to a much higher computation cost. This is where neural networks clearly outperform all forms of regression. You can reproduce these results with our notebook, differentialregression.ipynb, available on our GitHub repo, Differential Machine Learning. It is designed for Google Colab, so you can also run it directly with a shortcut, tinyurl.com diffregnotebook. It is essentially an article with code, which covers differential regression with all implementation details and optimized Python code. In dimension 10 and above, the program stalls, runs out of memory, and eventually crashes. Regression is vulnerable to the curse of dimensionality, and differential regression doesn't give us a silver bullet. Neural networks are much more resilient, but training also becomes significantly slower and less reliable in high dimension, say around 30 to 50. So, for real-world problems in finance where dimension routinely exceeds the hundreds, dimension reduction is a critical step in all situations. Brian and I specifically address dimension reduction in our upcoming article, Axes That Matter, PCA with a Difference, where we develop safe dimensional reduction techniques based, once again, on differential data. For example, we know that our basket option problem is reducible to dimension 1, but how can we figure this out automatically from data?
Our brief introduction to differential machine learning in the context of linear regression quickly hit the curse of dimensionality and naturally lead us to the problem of dimension reduction. Real-world problems in finance are often high-dimensional. Consider, for example, least square Monte-Carlo in the context of a labor market model, a high-dimensional, non-Markov interest rate model where the state X consists of a collection of forward rates of maturities up to some terminal date. In a 30-year problem with quarterly LIBORs, dimension is 120. Linear regression is therefore intractable. Instead, most implementations perform regression on a small number of fixed functions of the state, generally called features, and often called regression variables in the context of LSM. The choice of these regression variables is usually fixed manually and hard-coded in the implementation. One reasonable strategy is to pick a few swap rates on the curve, like 3 months, 2, 10, and 20 years, but there is a potential to miss the value and risk of certain transactions, like a 10, 15, 20-year butterfly. What would be really useful is an efficient algorithm to automatically pick the relevant regression features with safety guarantees. Another example is learning the value and risk of netting sets or trading books for regulations like XVA, CCR, or FRTB. This can be seen as an extension of least square Monte-Carlo, where the value of trading book is learned by regression or otherwise as a function of a high-dimensional state simulated in a hybrid model of all relevant asset classes. It is often necessary to reduce dimension, for example, for regression. Or it is desirable, for example, for neural networks, who learn much faster and more reliably in lower dimension. This means design an encoder function g from Rn to the lower dimensional Rp such that L equal to g of x encodes the state x in a lower dimension p. Of course, we want a safe encoding with minimal loss of relevant information. This is the same problem as picking regression variables in LSM, but it should be clear that handcrafted rules don't scale to trading books, as an algorithm is necessary. We really have two families of solutions when faced with high-dimensional problems. One, switch to modern machine learning models like deep neural networks instead of regression. Two, safely reduce dimension. These are in fact two faces of the same coin, because neural networks implicitly perform meaningful nonlinear dimension reduction. To see this more clearly, consider a vanilla feed-forward regression network, for example with 4 hidden layers. It consists of the input layer in yellow, whose units encode the high-dimensional state x, 4 hidden layers, h1, 2, 3, and 4, in blue and green, and an output layer in orange, whose single unit encodes the result v. The output layer is a linear function of h4 with learned weights w4. That is a linear regression on the features encoded in the units of h4, which themselves are a nonlinear function g of the input layer gx. The units of h4 therefore encode the regression features learned by the ANN. The encoder g is learned from data and encoded in the hidden connection weights. So a neural network is essentially a dimension reduction algorithm. Training an ANN means finding the regression features that matter for given labels. Contrarily to classic regression, those features are not fixed, but learned from data and encoded in the hidden connection weights. To learn those features is the whole point of the neural networks. This is what makes them robust in high dimension and qualifies them as artificial intelligence constructs. Differential neural networks, in particular, are capable of learning very effective regression features from differential data. Intuitively, this is because differentials contain critical information about what matters for a given target. We'll formalize this notion and call it relevance. Differential neural networks, also called twin networks, were introduced in our October 2020 risk paper, Differential Machine Learning. It is also available on Arxiv and SSRN. We also presented them last year on QuantMinds. In case you missed the presentation, the recording is available on YouTube with closed captions. In what follows, we explore explicit dimension reduction, that is, the design of safe encoders L equal to g of x, and more specifically, linear encoders of the form L equal to cap g times x. Although ANNs are robust in high dimension, they are more effective in lower dimension. In dimension up to 30 to 50, they are usually trained in around 100 epochs without any supervision. Higher dimension often requires a much larger number of epochs and manual tinkering. Safe dimension reduction is either necessary or desirable in all situations, and best implemented as a systematic preprocessing step.
So, how can I reduce the dimension of a given problem automatically, safely, and effectively? Safely means that I don't want to truncate information that could be relevant for the problem. And effectively means that I still want to reduce dimension as much as possible. The classic approach to dimension reduction is principal component analysis, or PCA. PCA has been extensively applied, including in finance, although it is not, in my opinion, a correct approach to risk management. To appreciate why, let me briefly recall how PCA reduces dimension. Consider your dataset X as a cloud of points located by the state variables xj in the standard coordinate system. The variances of the state variables xj measure the dispersion of the data, also called variation, along the standard axis, and the covariances measure linear dependencies between the projected coordinates. Alternatively, I can rotate the coordinate system and locate the same data points by their coordinates in the rotated basis, and again measure variations and covariations along the rotated axis by the variances and covariances of the new coordinates. When I rotate the coordinate system, variations change, but their sum is always the same. This invariant is called the total variance, and different rotations decompose the total variance along different axes. Among all the possible rotations, some particularly interesting ones are those where covariation is zero, so coordinates are mutually uncorrelated and the total variance is decomposed on axes of orthogonal variation. It is well known and easily demonstrated that a coordinate basis with orthogonal variation is given by the normalized eigenvectors of a covariance matrix Cxx of x, where the corresponding eigenvalues measure the variation along the rotated axis. PCA reduces dimension by truncating coordinates with low variation, drawn in red, thereby approximately locating data points, drawn here with cyan circles, only by their coordinates along the axis of high variation, drawn in blue. In practice, the dimension of a truncated subspace is often set such that the cumulative truncated variation, measured by the sum of the truncated eigenvalues, does not exceed a given tolerance epsilon. It follows that the variance of a reconstruction error, the distance between the original data points and their lower dimensional codes, is by construction lower than epsilon. In fact, PCA reduces dimension by minimization of a reconstruction error. Now, this is exactly why PCA is not the right approach for risk management. I don't really care about how well I reconstruct the state X or what are its main axes of variation. The information I really don't want to lose is how the state X affects my transaction or my trading book. Consider, for example, a spread option on x2 minus x1. Under the Gaussian assumption, it only depends on the underlying spread. So its gradients z are all aligned with the anti-diagonal. With a highly correlated dataset drawn here, gradients are almost aligned with the low variation axis truncated by the PCA, drawn in red. PCA reduced dimension by projection on the high variation axis drawn in blue, but the coordinates of the gradients on the blue axis are almost zero. It follows that the transaction is almost constant along the blue axis. As far as the spread option is concerned, all the states on this axis are in fact the same state. In this example, the low variation axis truncated by the PCA happens to be almost aligned with the direction that matters most for the transaction. So PCA completely misses the value and the risk of a spread option, and the low dimensional encoding given by the coordinate of a state X on the blue axis is completely useless in the context of this transaction. In fact, what this picture suggests is that I really should align the coordinate system with the gradients and then truncate the axis where the projected gradients are immaterial. By construction, the transaction is nearly constant along those axes, so the coordinates along those axes do not affect its cash flows, value, or risk. By truncating those axes of low relevance, I am effectively reducing dimension by projecting states on the axis where the magnitude of the gradients is maximized. So the state coordinates along these axes are those that matter most for the transaction. I will call the relevance of a given axis the magnitude of the gradient coordinates, by opposition to variation, which is the magnitude of the state coordinates. By truncating axes of low relevance, which in this example are also axes of high variation, I lost information on the state X, and I can no longer reconstruct it accurately. My low-dimensional encoding locates states by their coordinates on the high relevance axis drawn in blue at a large distance from the original states, as you can see. But those reconstruction errors do not matter for the transaction. The magnitude of its directional derivatives on the error axis is immaterial. Hence, the original state and the projected state are in fact almost the same as far as the transaction is concerned, irrespective of how far they may be located. So, classic PCA is fundamentally inadequate for risk management because PCA is one size fits all. PCA is a completely unsupervised algorithm. It works only with the state X and disregards any kind of labels. It follows that PCA reduces dimension without regard for either cash flows, value, or risk. Its low-dimensional encoding L equals GX only reflects the distribution of X, and it is identical for all transactions. For example, PCA gives the same dimension P and the same p-dimensional encoding L of a state X for an option on a basket or a basket of single stock options. But we have seen that a basket option only depends on one feature of a state, the underlying basket, so dimension is reducible to 1, at least under the Gaussian assumption, whereas the basket of single stock options depends on multiple features, so dimension is generally not reducible to 1. In both cases, PCA only reduces dimension according to the sampling distribution of a state S. It follows that PCA is ineffective. It does not reduce dimension as much as is possible for a given problem. More importantly, PCA is unsafe. As you have seen, PCA may well truncate very relevant coordinates of a state in situations where high relevance aligns with low variation. It is not only PCA that is potentially unsafe, but all one-size-fits-all dimension reductions. For any truncation independent of transaction data, there exist derivatives which value and risk will be missed. Just consider a transaction with positive value in the truncated space and zero everywhere else. So the only safe truncation is no truncation at all. PCA is ineffective and unsafe precisely because it is completely unsupervised. This means that you are going to need a supervised dimension reduction. PCA was extended in many ways in literature, including nonlinear variants like kernel PCA or autoencoders, but all those extensions remain unsupervised. So what you need is a different variant. The main idea again is to leverage differential data as customary in differential machine learning. The magnitude of a derivative zj of a target y with respect to the state variable xj is directly related to the notion of relevance, how much xj matters for the determination of a cash flow y. It is therefore natural to look for a safe dimension reduction algorithm based on the differential data Z, and this is the central notion of differential PCA.
I'm going to show how dimension can be safely truncated with differential data. Let me start building intuition with simple examples. Suppose that you're working with the dataset displayed here, where Z3, the partial derivative of y with respect to x3, happens to be identically 0. Clearly this means that x3 doesn't affect y in any way, so x3 is absolutely useless in this problem. I can safely remove it, thereby reducing dimension from 3 to 2 without affecting the problem whatsoever. Of course, it's rarely that obvious. Consider now a different dataset without any obvious truncation opportunity. A closer inspection, however, reveals that a fixed combination of the derivatives z1 plus 2z2 minus z3 evaluates to 0 in all examples. This means that the directional derivatives along the axis of direction 1, 2 and minus 1 are identically 0. In a rotated coordinate system aligned with v, the coordinates of x along v are therefore irrelevant. I can safely truncate it and locate states by coordinates along two axes orthogonal to v, and again safely reduce dimension from 3 to 2. Two examples illustrate safe dimension reduction by truncation of axes of immaterial directional derivatives. It is formalized with the notion of relevance. The relevance of some axis u is the magnitude of the projected coordinates of the gradient z on u. Differential PCA finds an orthonormal basis of Rn where the coordinates of the gradients are orthogonal. One such basis is given by the normalized eigenvectors of the covariance matrix CZZ of the gradient z, with relevance measured by corresponding eigenvalues. Differential PCA rewrites the dataset in terms of this basis and truncates coordinates with immaterial relevance, as measured by the eigenvalues. The practical implementation of differential PCA is an almost trivial modification of classic PCA. Once I know exactly what I want to do, it turns out to be very easy to realize. Classic PCA ranks axes by variation, whereas differential PCA ranks them by relevance. Classic PCA rewrites the data in the coordinate basis of the normalized eigenvectors of the covariance matrix CXX of the state variables x. Differential PCA uses the eigenvectors of the covariance CZZ of the gradient z. The reason for those rotations is to obtain orthogonal coordinates of the states x with classic PCA or the gradient z with differential PCA. So, for classic PCA, the eigenvectors p refer to CXX, whereas for differential PCA, they refer to CZZ. With this difference in mind, the implementation is identical. Dimension reduction is obtained by sorting eigenvalues in decreasing order and truncating the eigenvectors corresponding to the q smaller eigenvalues with cumulative value bounded by a given threshold epsilon. The truncated matrix P tilde combines the change of basis with the truncation. P-dimensional state encodings are given by L equal to P tilde transpose times X. Reconstruction of the original state is given by X tilde equal to P tilde L. Reconstruction simply rewrites the coordinates of L in the standard basis. Of course, the truncated information cannot be recovered. So X tilde is P tilde transposed, X, or simply the projection operator pi times X. The reconstruction error is X minus X tilde, which is the identity minus pi times X, or the error operator sigma times X, which is the projection operator in the error space. In process states X into low-dimensional codes L, I also need to rewrite differential data Z in terms of the differential with respect to L. Denote S the gradient of Y with respect to L. By an application of the chain rule for derivatives and some basic algebra, S equals P tilde transpose times Z. Notice the same operator that projects states X into L also projects differentials Z into S. Therefore, the reconstruction of Z is given by P tilde times S, which is pi times Z, and again the error is sigma Z. Although the implementation of classic and differential PCA are identical except for the covariance matrix, the actual transformation is a very different one, as you have seen on the animation. The projector pi of classic PCA implicitly minimizes reconstruction error sigma x, whereas differential PCA minimizes sigma z. Classic PCA guarantees correct state reconstruction, but it may cause significant axis of risk, whereas differential PCA guarantees correct reconstruction of risk, but it may lose information for reconstructing states. So, the implementation of differential PCA is a rather trivial exercise, but of course an algorithm is only as good as its guarantees. Let me now proceed by demonstrating the safety, effectiveness, and computational efficiency of differential PCA in more precise terms. Let me start with safety. Differential PCA guarantees that the magnitude of truncated risk is bounded by epsilon. Recall that we are working with samples y and pathwise differentials z, not prices v, and risk sensitivity is delta. The price v is a function of the Markov state x given by conditional expectation of y given x. Provided appropriate smoothing, this also applies to risk sensitivities delta equal to dv dx. They are the conditional expectations of pathwise differentials z given x. The guarantee is that the magnitude of truncated risks in L2 is less than the magnitude of truncated differentials, which by construction is bounded by epsilon. It follows by a first-order expansion argument that the approximation error on prices v due to truncation is also bounded by epsilon times the variance of x. Those results are demonstrated in the paper and express that differential PCA is safe in terms of value and risk approximation. In particular, price and risk functions learned from truncated data are correct within a small quantified approximation error. So, differential PCA is safe. Let me now demonstrate that it is effective, that is, when the transaction or trading book actually depends on a small number of risk factors. Differential PCA correctly identifies the number and the nature of the risk factors. Suppose that the final cash flows y only depend on one feature of the initial state x, like a basket option under the Gaussian assumption. This means that y is a function of the feature v dot x and w, where v is the only direction that matters, for instance the weights of the basket. W is noise independent of x. Then by a straightforward application of the chain rule, z is equal to y1v, where y1 is the partial derivative of y with respect to its first argument. This equals y1 norm of v times v over its norm. The left term y1 norm of v is a random number, and the right term v over its norm is a fixed vector. It follows that the covariance of z is of rank 1, with only one eigenvalue given by the L2 magnitude of the left term, with normalized eigenvector v over its norm. Therefore, differential PCA correctly performs a one-dimensional reduction where the axis is correctly given by the underlying basket. More generally, if the cash flows y depend on p linearly independent features of the state x, that is, y is a function of v1.x, v2.x, up to vp.x, and the independent noise w. Now differential PCA finds a p-dimensional reduction whose bases u1, u2 up to up span the same space as the vectors v1, v2 up to vp. The general result is demonstrated in the paper along the same lines as the one-dimensional result we just saw. So differential PCA correctly identifies the principal risk directions. What differential PCA cannot guarantee is how much dimension is reduced. Some problems are not linearly reducible, and I will not recommend reducing dimension aggressively. That is, increase the threshold epsilon to achieve larger reduction at the expense of safety. This being said, we empirically observe that the differential PCA often truncates dimension by a maybe surprisingly large amount in the context of complex transactions and real-world trading books. The interpretation is that those books are often dominated by a small number of large risks. Whenever dimension is reduced under something like 7 to 10, lightweight regression is applicable, and differential regression is the recommended tool, especially since differential data is already available from the differential PCA. If not, differential PCA tells you that the problem cannot be linearly reduced enough to enable regression. You need nonlinear dimension reduction, that is neural networks, or ideally the differential networks. One key comment is that the differential PCA is very helpful nonetheless, because neural networks are trained much faster in a much more stable manner in lower dimension. Therefore, differential PCA is useful in all situations as a pre-processing step. What is the development and computation cost? If you have access to differential data, there are basically no development cost because differential PCA is PCA on differential data. The computation cost of differential data is small with AAD. The cost of differential PCA is dominated by two computations. First, the covariance matrix CZZ of cubic complexity. A high-performance library like Intel's MKL computes the covariance of 32,000 examples in dimension 1000 in a fourth of a second on a standard workstation. Second, the eigenvalue decomposition, also of cubic complexity. MKL computes the eigenvalues and eigenvectors of a symmetric square matrix of size 1000 in 50 milliseconds. As you can see, differential PCA is extremely fast, and since it is also safe and effective, it constitutes an essentially zero-cost pre-processing step with considerable benefits. Before I hand over to Antoine to conclude the presentation, let me briefly comment on the covariance matrices I kept talking about. Differential PCA is essentially the eigenvalue decomposition of the covariance matrix of Z. Does it mean the second moment expectation of Z transposed, as noted on previous slides, or is it the usual central covariance matrix? The central covariance matrix is obtained by prior subtraction of the means of Z, in which case I get what I call central differential PCA. By subtracting the means from the differential series, central covariance effectively zeroes out constant gradient coordinates, that is, the linear risks. Therefore, the eigenvalues of central differential PCA measure the magnitude of nonlinear directional risk, by contrast to differential PCA, whose eigenvalues measure the magnitude on directional risk, both linear and nonlinear. The significant eigenvectors of central covariance therefore correspond to the principal axis of nonlinear risk, and axes of linear risk are truncated, no matter their magnitude. By contrast, non-central differential PCA only truncates axes of immaterial risk. In general, I want to pick all directions of material risk, linear or not, and work with non-central differential PCA. Central differential PCA is, however, a very useful tool to identify and quantify nonlinear risk axes. For example, one effect of central differential PCA is to remove delta hedges from the analysis of trading books, effectively exhibiting the risk factors of the naked options of hedged portfolios.
Let me conclude with some interesting applications of differential dimension reduction. The first and most evident application is the selection of regression variables in the least square Monte-Carlo, or LSM. Recall that LSM estimates future prices by regression of cash flows Y. The choice of the regression variables, however, largely remains an open problem, most often tackled with handcrafted rules, hard-coded in the implementation, and manually maintained, for example where the model is upgraded or when the procedure is applied to different kinds of transactions. This is based on more or less reasonable guesses, prone to error, and hard to scale to complex models or complex transactions, and certainly to trading books. Differential PCA provides a direct and explicit solution by finding the correct regression variables automatically in a principled and effective manner with safety guarantee and a lightweight and efficient implementation. It requires differential data, of course, but differential data is computed efficiently and automatically by instrumenting LSM simulations with AED. Because differential PCA learns regression features from data, it automatically adapts to the simulation models and cash flow schedules of arbitrary complexity, and seamlessly scales to complex exotic or hybrid transactions, including trading books. Differential PCA finds the minimum number of regression features, so the implementation can assess whether linear regression is possible or not. When the dimension is not reducible enough to enable linear regression, the implementation knows that at runtime from differential PCA, so you can throw an exception or automatically switch to more sophisticated ML models resilient in high dimension like neural networks. So, in the context of least square Monte-Carlo, differential PCA nicely ties up some loose ends that have been around for a long time. In addition, differential regression provides a sharp improvement over classic regression. Since differential data is necessary for differential PCA anyway, you may as well reuse it for a much more effective differential regression. A second application is preprocessing datasets for all kinds of machine learning. Linear regression only works in low dimension, but all ML algorithms work better in lower dimension. And since differential PCA is fast and lightweight and comes with a safety guarantee, it is essentially a zero-cost preprocessing step and often a very beneficial one. We have implemented differential PCA as a systematic preprocessing step, and we never looked back. Finally, let me mention a more abstract and perhaps somewhat philosophical application for the design and application of derivatives models. Capital markets are extremely complex systems. Even if I could model every aspect of a financial market correctly, the model would be computationally intractable. Every derivatives model is a simplification of a complex reality. So modeling involves a choice. What are the critical features of a market that I must absolutely model correctly, and what are maybe less critical phenomena that I can simplify. And this is a form of dimension reduction, so differential PCA can help. It tells me what are these critical features that matter most to a given transaction or trading book, so I can reliably specify or calibrate my pricing models. By revealing the principal risk factors, differential PCA helps me better understand and therefore better manage my derivatives risks. As a final example to illustrate this point, consider industry practices for Bermudan options in the early 1990s. At the time, Bermudan options were widely managed as one-factor products, only dependent on so-called coterminal swaps from early exercise dates to maturity. Models were often calibrated only to coterminal swaptions. I even came across some models of a distribution of coterminal swaps entirely ignoring the rest of the yield curve. In 2001, Jasper and Life demonstrated that Bermudan options also depend on short rates, and to ignore short rate volatility implied by caplet prices may lead to inaccurate pricing, ineffective risk management, and even incorrect conclusions. Claims were made in literature that Bermudan options are more valuable in more realistic multi-factor models. In fact, this is an artifact due to calibration to only coterminal swaptions, where decorrelation of interest rate implicitly increases caplet prices above market value. But with models correctly calibrated to both coterminal swaptions and caplets, the contrary is generally true. Bermudan options are less valuable with lower interest rate correlation due to a monotonic relationship between correlation and forward volatility. All of this is well known now, and Jasper and Life were right, of course, but at the time it was a heated debate involving some of the biggest names in the industry. Differential PCA did not exist, of course. AAD was only introduced to finance in 2006 in Giles and Glasserman's Smoking a Joint risk article. But if it had existed, it would have given the answer and thereby closed the debate. Here I simulated a Bermudan option dataset in a 5-factor Chayet model. This graph displays the eigenvectors of classic PCA in terms of zero coupon yields scaled by square eigenvalue. PCA clearly exhibits 5 independent deformations. The 3 main deformations expectedly correspond to shift, steepening, and convexity, and we see that we have little variation on the 5th factor. For a European swaption, differential PCA correctly identifies only one material risk factor, corresponding to the underlying forward swap. For a Bermudan option, differential PCA clearly identifies 2 meaningful features of a yield curve, a long-term factor corresponding to coterminal swaps and a short-term factor corresponding to rates underlying caplets. Differential PCA shows that these 2 risk factors cannot be combined. Models must correctly represent the joint dynamics of the 2 factors, and hedge strategies must simultaneously cover the 2 principal deformations. In particular, models must calibrate to both long and short-term rate volatility. Thank you very much for your attention.